Hello everybody, this is Mr. McAllen again, and I'm on the last video of a four-part series for finding derivatives implicitly. And we started off with an implicit equation for an ellipse in the last video. And now our goal is what if we're asked to find the second derivative of this function? Well, in order to get to the second derivative, you would have to use implicit to get to the second derivative. So in this case, we've already gotten to the point where we found the first derivative. Then we would carry on and take the second derivative. So in case some people tune in and they didn't see that first part, I'm just going to go through that rather quickly. So I'll just show how we got to the first derivative first, and then I'll do the second derivative, so because it follows the same procedure. So if you've already seen this, you can just fast forward ahead. But we'll use the operator here, d dx, both sides, and we're going to have, this will be 6x plus 2y, y prime, minus, I'm just going to do the derivative of xy, and that will be 1y plus, and this would be x, y prime, and that's all can be 0, and I'm going to distribute. And then I'm going to separate those terms, so and I'm moving the terms to the right. So those are gone. And I'm going to factor out the y prime. And I'm going to divide out those terms. Now, well, of course, we just want to double check, make sure we match what we got before, because I was kind of rushing through that. And now I want to take the second derivative. So to take the second derivative, I use a differential operator again, d dx. And I'm going to do d dx over here. And when I do that, I get y prime prime equals, and I'm going to have to do the derivative on this side, and I have a quotient rule. So I've got to just remember the quotient rule. Remember, the quotient rule is f prime g minus g prime f all over g squared. So when we do that, we've got to be extra careful with functions that have y's in them so that we turn them into y primes. So we'll do the derivative of the top. The derivative of the top numerator is going to be 6 minus 3y prime. So remember, this term right here was a y function, so we've got to turn it into y prime, a dy dx. And we're going to multiply that by the denominator. Now we've got to subtract from it. I need to make some room here, so forgive me. I've got to take the derivative of the denominator, which is going to be 3 minus 2y prime being multiplied by the numerator, 6x minus 3y. That's all going to be over the denominator squared. Now, some people look at this and they're a little bit fearful of what type of simplification we can do, but typically when we have a problem like this, we're trying to figure out what y prime is equal to. So remember, they gave us, in the beginning of the problem, they gave us a point. This is on the last video. They gave us a point at 1, 4, and they asked us about tangency and a normal line at 1, 4. So what we know is, we know the x value, we know the y value, and from before we also knew that at the point 1 comma 4, we knew that y prime at x equals 1, y equals 4, we knew that was equal to 6 over 5. So now we have everything we need to figure out what y prime prime is. So what you would do is you would plug in, and this might take a while, but you would just plug in 6 minus 3 times 6 over 5. Basically it's just a crazy problem of plugging in values to figure out what y prime is. And then we would plug in 3 times 1 for x, minus 2 times 4 for y, minus, we've got 3 minus 2 had to make a little room there. So that's what we would have to do to figure out what y prime prime would be equal to. And it may require a calculator. It may require doing a bunch of arithmetic. But typically, they just want to find out what the function's concavity would be at that point, or what the second derivative value would be. There's a whole variety of uses for the second derivative at that point. In this case, I'm expecting the value of the second derivative to be negative, because this curve at 1 comma 4 is got downward curvature, and we should get a negative value when we plug in all these values. But for the primary importance of this video, finding the second derivative, I think our objectives have been met. And you can see here how complicated the equation looks, but if you have the x value, the y value, and the derivative value at the points, you can plug them in rather quickly and solve for those values. Hope this video was of help to you, and I look forward to your comments. Have a good day.